In this video, we're going to take a look at a coding interview pattern called breadth first search, or short as BFS, and tree traversal. So we also call this pattern level order traversal, right? So the goal I want to make this video is I want to focus on understand the pattern rather than just doing a bunch of Leetcode problems. I want to focus on understand a specific patterns in detail so that we can build the concepts around this pattern so that we can be able to apply the same concepts to other problems on Leetcode, right? So that are related to breadth first search pattern or level order traversal pattern. Once we understand the pattern, once we understand how we can deal with questions that are similar to this, we can then be able to apply the same concepts to other Leetcode problems. And we're going to solve some of the problems that I chose related to BFS in this video. And hopefully by the end of this video, you can be able to get really good at BFS or breadth first search or level order traversal code interview pattern. So the goal for this breadth first search was that we want to traverse the tree level by level, right? So given a binary tree, we want to traverse this level by level instead of traverse in depth. And we usually use a queue to keep track of all the nodes of the next level before we jump onto the next level, right? Before we traversing the next level. So we usually going to do this level by level, and the space complexity for using this, for using BFS or for using level order traversal is going to be big O of m, where m is the maximum number of nodes for all the levels in the tree, unless we're saving each and every single node onto a list. But if we're not, we're just traversing each and every single node in the tree using BFS, then the space complexity is going to be big O of m. So let's take a look at the first problem. So the first question that we're going to take a look at is a binary tree level order traversal. So given a binary tree, we want to return the level order traversal of its nodes value. So from left to right, level by level. So for example, we're given a binary tree like this, and we're asked to traverse this level by level. And in this case, at the end, we're returning a list of each level's nodes value, right? So in this case, the first level we have 3, second level is 9 and 20, and the third level is 15 and 7. So whenever we get a question like this where we want to traverse this binary tree or traverse a graph level by level, we want to use a queue to keep track of all the nodes that we have for the next level that we're going to traverse, right? Where before we jump onto the next level, we want to get all the nodes that we have for that level onto the queue. So in this case, what we're going to do first is we're going to add the current root node onto the queue, and we're going to traverse this by saying while the queue is not empty, we're just going to traverse all the nodes that we have in the current queue, right? Because we know that all the nodes that we have in the current queue is what we have for the next level. So in this case, we're just going to traverse that and then remove that off of the queue. Then what we're going to do is we're going to add the current node's children onto the queue so that we can be ready for the next iteration, right? So for the next iteration, we're going to traverse the next level, and then we're going to add its children onto the queue, and then remove that node off of the queue. So it will look something like this. So first we're going to add the current node, right? The root node, which is 12, onto the queue. So in this case, we have node 12, right? So which is on the queue. And then we're just going to remove that off of the queue, and then we're just going to add its children 7 and 1 inserted onto the queue. So then we're going to have a size of 2, right? Now we have the current level size of 2, because that's how many nodes we have in the queue. And then we iterate that, so we only iterate 2 times, right? And then we're going to get each and every single node, all the nodes that we have in the queue, right? So currently, and remove them off of the queue, and then just add its children onto the queue. So now we have 9, 10, and 5. And we remove those visitor nodes off of the queue. So now we have 9, 10, and 5. And the second level is 7 and 1. And now we have 3 nodes in our current in our next level, 9, 10, and 5. And then we're just going to add them onto the list, removing them off of the queue. And then we also have to get those nodes children added onto the queue. In this case, there are no children for those nodes. So in this case, our queue is empty. Our job is done. We can return our list. So to do this in code, we're going to have a list of list integer. We're going to call it result list. So then what we're going to do is we're going to define our base case, right? Because there could be a situation where the root is null. So if root is null, we can just return our empty list. So then we're going to add our queue, which is going to be the tree node, right? Which is going to be a type tree node, because we're going to store the next level's nodes, right? All the nodes that we have for the next level. So we're going to say queue.add root, because that's the next level that we're going to traverse. So while queue is empty is equal to false. So while queue is not empty, we're just going to have a variable that keeps track of the current size, right? So queue.size. So we're going to iterate that number of times, right, from 0 to size, and we're going to do the procedure that we talked about by removing that element off the queue, adding its children onto the queue, and then we're also going to add the current nodes onto the list. So that's why we're going to have I is equal to 0, I is less than size. We're going to iterate, right? So we're going to have a list of integer that we're going to, which is going to be all the current nodes value. We're going to add it onto this list. So then what we're going to do is we're going to remove that element, remove the first element of the queue. So first is equal to queue dot right, which will remove the first element of the queue, and then we're just going to add it onto the sublist. Then we're going to see if first.left does not equal null, because we want to make sure that we do not add null value onto the queue. So if it's not null, we're going to add queue.add first.left. And if first.right does not equal null, we're just going to add the first.right onto the queue as well. So queue.add first.right. And then what we're going to do is we're just going to continuously do that for a size number of times. And then at the end, once we've done the iteration by getting all the elements children added onto the queue and the current elements value onto the sublist, we're just going to get the current sublist added onto the result list. And at the end, we're just returning the result. So let's try to run the code. Okay, so let's try to submit. And here you can see we have our success. So this is how we solve this Leetcode problem, binary level order traversal. The first problem, the time complexity in this case is going to be big O of n, where n is the number of elements that we have in the tree, right? And the space complexity in this case is also going to be big O of n, because we're using a we're using a result list to store each and every single nodes for each and every single level. So in this case, it's going to be big O of n for space and time complexity. So let's take a look at another problem. So now let's take a look at another question that tests our knowledge in level order traversal. So given a binary tree, return a zigzag level order traversal of its nodes value. So from left to right, then right to left, then for the next level, we're going to alternate between. So for example, given binary tree like this, we're just going to return its zigzag level order traversal. So in this case, it's going to be 3, 29, 15, and 7. Right, so we're going from left to right, then right to left, then left to right again. So this is another question that's very similar to the level order traversal that we did. So we're just going to use the same code. But the thing is that we want to determine how can we change this code that we used to solve the previous problem to solve this problem, right? So this is our previous problem code, right? We're basically adding each and every single element for the next level onto the queue, so that when we traverse the next level, we're going to add its next level elements onto the queue and removing the current elements that we have on the queue off of the queue and add it onto the list, right? So basically, we're doing the same thing. We're doing level order traversal, but all that matters is how we're going to add the current element onto the queue. So what we're going to do is we're going to have a variable called, it's going to be a Boolean, is left to right. So this is left to right variable by default is true because we're starting from going from left to right. So if it's left to right, we're just going to add the element onto the list regularly, right? Just the way how we add the list normally. We're just going to add a list from left to right. Okay, so if is left to right, what we're going to do is we're just going to add the current element onto the list, right? In this case, adding the current element onto the list is going to be appended onto the last from left to right, right? So if the is left to right is true. Otherwise, if it's not true, what we're going to do is we're going to add it onto the first, like add it basically from the right to the left instead of the right to the left, right? Sorry, instead of left to the right, we're going to add it from right to the left by inserting from the first element, right? Inserting from the very first element. So insert it from very left. So first dot val. So we don't really care about how we're going to like adding its children. We just care about how we're going to add the current element onto the sublist. So to add the current element on the sublist, we're just going to have a variable that keeps track of the current direction. And after it's done, we're just going to say is left to right is equal to is left to right, the opposite of it, by simply adding an exclamation mark right here. So in this case, basically we're just going to add 3, right? We're going to add 3 onto it. And then for the next level, we have 9 and 20, right? So we're just going to say, in this case, we're going to add it from right to left. So then we going to have add 20 on the first element in the sublist, right? And then we're going to add 9 onto the first element in the sublist. Okay, or sorry, I should say the first 9 to be the first element on the sublist. Then we're going to add 20 as the first element in the sublist. So now we have 20 and 9, right? Just like what we have here. And then for the next level, we're going to have 15 and 7, right? So 15 and 7 in our queue. Then we're basically just going to go from left to right. So we're going to say 15 added onto the list, then 7, right? So we're going from left to right for the sublist. So let's try to run the code. And let's try with a few more test cases. So let's say we have 1 here, 2 here. Okay, let's try to run the code and submit. So here you can see we have our success. So basically this is how we solve this zigzag level order traversal by simply adding a variable to change the direction where we're going for each and every single direction, right? So this is another level order traversal question. So let's take a look at another one. So now let's take a look at another question called average of levels in binary tree. So given a non-empty binary tree, return the average value of the nodes on each level in the form of an array. So here you can see we have a binary tree, and then 3, 9, 20, 15, 7. So for each and every single level, we want to get the average of those nodes values. So for the first level, the average is 3. The second level is 9 plus 20, which is 29. 29 divided by 2, which is 14.5. And the third level is an average of 11, right? So in this case, we're just going to return that in a list of doubles. So this is a question of level traversal. We're traversing this level by level. And then we're just going to get the sum as well as the size of the current level. Then we're going to use the sum of the current level, the sum of all the values add up, which is the sum of the current level, divided by the size of that level, which is going to be the average of that entire level, right? So in this case, what we're going to do is we're going to implement the level order traversal. So we're going to have a list of double. that we're going to return at the end. So then we're going to have a queue, right? So we have a queue that basically stores the nest levels tree node. And then what we're going to do is we're going to add the nest level elements onto the queue first, which is basically the root, right? Then while the queue is not empty, what we're going to do is we're going to iterate. First, we're going to get the size, which is equal to q.size. And just like how we did it in the previous question, we're going to iterate size number of times, right? So in this case, we're going to iterate all the elements that we have in the queue, right? And then we're just going to get that element out of the way, add it onto the sum, and then we're going to add its children onto the queue, and then so that we can traverse the next level, right? So we're going to have a double Okay, so we're going to have to iterate for I is equal to 0, I is less than size, so I plus plus. So we're just going to first remove the first element off of the queue. So in this case, tree node first is equal to q.remove, which will remove the first element off of the queue. And then once we remove the first element off of the queue, what we're going to do is we're going to add its children onto the queue, right? So in this case, if first.left is not equal to null, then we're just going to add it onto the queue. And if first.right is not equal to null, just going to add it onto the queue, and add the right child onto the queue. So once we add its children onto the queue, then what we're going to do is we're going to get the current element plus the sum. So sum is equal to sum plus the current element's value, or current node's values, right? So sum plus equal to first dot val, right? So then what we're going to do is we're going to continuously do that until we get our sum as well as our size, and we're ready to traverse the next level. Then we're going to get the answer, right? So in this case, it's going to be the average is equal to sum divided by the size. So we're just going to add that onto the result list and move on to the next iteration, right? So let's try to run the code. We should have a 0.0. Let's have a 0.0. Okay, so this we got a accepted. Let's try to run submit. And here you can see we have our answer. So this is how we solve this Leetcode average of levels in binary tree. Well, let's take a look at another level order traversal problem. This problem can be solved using depth first search as well, but I'm just going to talk about how we can do this using level order traversal. Basically, we want to populate nest right pointers in each node, and we're given a perfect binary tree where all leaves node are on the same level, and every parent has 2 children. The binary tree has the following conditions. So we have a node n has a value in the left, the right, and the nest pointer, and we want to populate each nest pointer point to its right node. So if there's no nest right node, the nest pointer should point to null. So initially all nest pointer are all null for the binary tree, and this problem can be solved in binary level order traversal, because in this case we're just trying to get each and every single node point to the right node, which is on the same level, right? It's not like I wanted to get node 2 point to node 6, right? We're not on the same level. We want to point to the node that are on the same level. So node 2 pointing to node 3, node 4 pointing to node 5, node 5 pointing to node 6, node 6 pointing to node 7. We want to get the current node point to the right node, which is contains in the same level. So it makes sense to use a level order traversal to solve this problem. So basically, To solve this problem using level order traversal, we're just going to basically iterate each and every single like level, right, and traverse each and every single level, and we want to have a previous pointer, and that previous pointer basically points to the previous node, and we want to get the previous node dot nest going to point to the current node. And then what we're going to do is we're going to move on to the next node. And there's some base cases, there's some cases that we have to consider, right? Because there could be a situation where the current node is null. So that means that we also have to, in this case, we have to return null, right? So, and because we're given a perfect binary tree, we don't really care if there is node that's null. Like for example, if node 5 is null, then we want to get node 4 is pointing to node 6. That won't happen here because this is a perfect binary tree. Okay, so let's take a look at how we can solve this. So our first base case is that if root is null, right, that's our base case, then we're just going to return null because that's our base case, right? So we're going to have a queue that stores the node, right, the current levels node. So, and then we're going to say queue.add root. Okay, so that's our first level. And just to be clear that this method, this function, basically at the end we're returning the roots, right? We're finishing like changing the nest pointer to the nest node, and once we've done that, we're going to return the root node. Dot is empty. Sorry, queue dot is empty. So if queue is not empty, what we're going to do is we're just going to iterate basically number of times. Basically we want to iterate all the nodes that we have in the queue, right, that we have in the queue, and then for each iteration we're just going to adding its children onto the queue if they're not null, right? And we're going to make sure that we get the previous pointer .nest point to the current node, and we're going to get the previous we're going to get the current node assigned to the previous pointer, right? So we're going to have a size which is equal to queue.size. We have a node, and let's call it previous node, which is going to equal to null initially. We're going to iterate starting from 0 all the way to size. So for each iteration, we're going to remove the top element first element off the queue. First is equal to queue.remove. So then what we're going to do is we're going to getting the previous pointer, right, point to, so previous pointer.nest is pointing to the first node. But we want to make sure that if the prev does not equal null, we can do that. So prev.nest is equal to first, right? And then what we're going to do is we're going to get the previous pointer point to the first. Then what we can do is we can comparable to adding the current node onto, so the current node's children onto the queue. So in this case, if first dot left does not equal null, then we can adding its children, right? Because in this case we have a perfect binary tree, right? So first dot left, or I should say first dot right, doesn't matter. So if one of them is equal to null, then we're not going to adding their children because we know that both of their children is going to be null. If first dot left does not equal null, we're going to add both of their children onto the queue because we have a perfect binary tree. So let me just make a comment, because we have a perfect binary tree. Okay, so we're going to say queue.add first.left, queue.add first.right. Okay, then we're going to move on to the next iteration. So we're going to continuously do that until we basically have an empty queue. So let's try to run the code. Okay, so let's try to submit. And here you can see that this is how we solve this populating nest right pointers in each node, the Leetcode problem. And basically, we're just going to getting the nest node, right? The each node dot nest point to the adjacent right node. And to do that, we're going to have like a pointer, like a node pointer that basically keep track of the previous pointer so that we can get the previous pointer dot nest point to the current node. If we were to do this using Defer search, it's going to be a constant space complexity because it says that recursive approach is fine. We might assume implicit stack space does not count as extra space for this problem. So basically, if we were to use depth of search for this, we're going to get the current node, right? The idea is this: we're going to go from top to bottom, and then we're going to get the current node dot left is going to point to current node dot right, right? We're going to form this connection, and then what we're going to do is we're going to go from top to bottom, right? So we're going to move on to this side. Now we have node 2, and to form this connection, we're going to get node 2 dot left is going to point to current node dot right, and then we're also going to get current node dot right is going to point to node 6. And how can we do that? Well, what we can do is we can be able to, because we're standing on the parent perspective, right, node 2, we can get node 2 dot, or we can get node 2 dot right is going to equal to node 2 dot nest dot left. Does it make sense? Because we already formed this connection. So what we can do is we're going to get the parent help its children to form this connection by saying that parent dot nest dot left, right? And getting that node point to getting this node point to this node. So once we have forming this connection, we're going to continue to do the depth of search. In this case for node 4, in this case node 4 has no children, then our job is done, we can just return. And in this case we have node 5, and node 5 has no children because we're just basically standing from the parent node and then manipulating the connections. We're basically forming the connections standing from the parent perspective. So in this case, if the parent does not have any children, we can just return, and then we're done our path. We've done our depth of search, and then we're coming back to here, node 3, we're forming the connection. In this case, node 6 is pointing node 7, and node 7, since node 3 does not have any nest, the nest pointer is null, right? Node 3 is pointing to null. In this case, we cannot have nodes. We basically have node 7 pointing to null as well. So this is basically, I know it's kind of a little out of topic, but this is how we solve this using depth of search. So that is it for this video, and basically if you want more practice for that specific pattern, I have a section on my channel called Leetcode by Categories, which basically I sort all the Leetcode problems that I did in categories so that you can have more practice for that specific category. So that is it for this video, and thank you for watching.